For over a century, locomotives have been the iron backbone of American commerce. Massive machines weighing up to 400,000 pounds and containing enough recyclable material to make a scrapyard operator's eyes light up. A single diesel-electric locomotive holds approximately 12,000 pounds of copper wiring, 3,000 pounds of aluminum in radiators and engine components, and over 200 tons of high-grade steel in its frame and body. At current scrap prices, the raw material value of a retired locomotive can exceed $150,000. Yet across the remote stretches of the American West, from the high desert of Nevada to the plains of Wyoming, railroads are deliberately burying these mechanical giants in carefully engineered pits rather than sending them to recycling facilities. The practice seems to defy logic. In an era of environmental consciousness and resource conservation, why would corporations choose to enter valuable materials in the ground? The Union Pacific Railroad maintains several such burial sites on remote company property where locomotives that once hauled freight across the continent now rest beneath layers of earth and engineered fill. BNSF Railway has done the same, selecting isolated parcels far from public view where retired units can be permanently laid to rest. These aren't abandoned machines left to rust in forgotten sidings. These are deliberate, planned disposals carried out with the same precision that once characterized the locomotive's operation. The economics appear equally puzzling. Scrapyards across the country actively seek retired locomotives, offering to handle transportation and processing in exchange for the valuable materials within. The copper alone in a single unit's electrical system represents weeks of revenue for a medium-sized recycling operation. Yet railroad executives, intimately familiar with the value of every asset on their balance sheets, consistently choose burial over sale. The decision isn't made lightly, nor is it universal, but it happens with sufficient frequency that burial has become an accepted, if little discussed, aspect of locomotive life cycle management. The answer to this paradox lies not in corporate wastefulness or environmental indifference, but in a complex web of federal regulations, hazardous materials, and economic realities that transform these seemingly valuable machines into expensive liabilities the moment their wheels stop turning for the final time. The answer begins not with economics, but with a silent killer that transformed American industry in the late 20th century. Asbestos, prized for decades as the miracle mineral that could withstand extreme heat and provide superior insulation, was woven into virtually every locomotive built between the 1930s and the early 1980s. The fibrous material lined boiler insulation in steam locomotives making their final runs, wrapped around diesel engine exhaust systems, reinforced brake shoes that could stop 15,000-ton coal, trains and insulated electrical components throughout the machine. A single locomotive from this era could contain anywhere from 500 to over 2,000 pounds of asbestos in dozens of different applications, from the obvious to the hidden. Steam locomotives transitioning to diesel power in the 1950s were particularly saturated with asbestos. Engineers wrapped it around every hot surface, pressed it into gaskets, and molded it into fireproof barriers. Early diesel units followed the same philosophy, with manufacturers like EMD and General Electric specifying asbestos-containing materials throughout their designs. The Electromotive Division's GP7 and GP9 models, built by the thousands during the 1950s, featured asbestos in their dynamic brake systems, traction motor insulation, and engine room fire barriers. Even locomotives built as late as 1979 contained asbestos components, grandfathered in before regulations fully prohibited their use. The regulatory landscape shifted dramatically in the 1970s as medical evidence mounted. The Environmental Protection Agency began restricting asbestos use in 1973, culminating in increasingly strict regulations throughout the 1980s. The Asbestos Hazard Emergency Response Act of 1986 and subsequent amendments established ironclad protocols for handling, removing, and disposing of asbestos-containing materials. For locomotive owners, these regulations transformed retired units into ticking financial bombs. Professional asbestos abatement requires certified contractors, specialized equipment, negative pressure containment systems, and disposal at approved hazardous waste facilities. The cost of properly removing asbestos from a single locomotive ranges from $30,000 to well over $100,000, depending on the extent of contamination and accessibility of affected components. This cost alone often exceeds the scrap value of the entire machine. But the financial burden extends beyond abatement. Railroads face enormous liability exposure if workers or contractors are exposed during dismantling. Scrapyards, aware of these risks and costs, began refusing contaminated locomotives outright or demanding premium fees that eliminated any economic benefit of scrapping. The mathematics became brutally simple. A locomotive worth $150,000 in scrap materials might cost $200,000 to properly dismantle and dispose of, creating a negative value of $50,000 or more. The transition from environmental hazard to economic reality reveals why burial becomes the rational choice. When a railroad retires a locomotive, the costs begin accumulating immediately, long before any scrap revenue arrives. Transportation alone presents a significant hurdle. Moving a 200-ton machine from its final resting point in a railroad yard to a distant scrapyard requires specialized heavy-haul trucking or rail movement, permits for oversized loads, and route surveys to ensure bridge and tunnel clearances. These transportation costs typically range from $8,000 to $15,000 depending on distance, and that assumes the locomotive can move under its own power to a loading point. Dead units requiring cranes and specialized equipment push costs even higher. Before any scrapyard will accept a retired locomotive, railroads must conduct environmental assessments, documenting every hazardous material present. Beyond asbestos, these assessments inventory PCB-containing electrical components, lead-based paints applied in multiple layers over decades, residual diesel fuel in tanks and fuel systems, contaminated lubricating oils, ethylene, glycol coolants, and mercury switches in older electrical systems. Each identified hazard triggers specific handling and disposal protocols, adding layers of cost and complexity. Environmental consulting firms charge $5,000 to $12,000 for comprehensive pre-disposal assessments, and the resulting reports often reveal contamination levels that make conventional scrapping prohibitively expensive. The scrapyard itself, assuming one can be found willing to accept a contaminated locomotive, charges premium rates for hazmat handling. Standard scrap processing equipment cannot safely cut into asbestos-laden components or PCB-contaminated electrical systems. Specialized facilities equipped for such work are rare, and their fees reflect both the equipment investment and liability exposure. Processing fees of $25,000 to $75,000 are common, effectively consuming most or all of the scrap revenue before any metal reaches the recycling stream. For locomotives with extensive contamination, these fees can exceed $100,000, turning the entire transaction upside down. Railroad maintenance shops face their own calculus. Shop space is precious, dedicated to maintaining revenue-generating locomotives that keep freight moving and profits flowing. Every retired unit occupying a service bay or storage track represents opportunity cost, preventing productive use of that space. Insurance costs continue as long as the unit remains on railroad property, and liability concerns mount with each passing month. The longer a contaminated locomotive sits awaiting disposal, the greater the risk of unauthorized access, environmental release, or regulatory citation. Burial, by contrast, offers financial predictability. Excavating a properly sized pit on remote railroad-owned land, positioning the locomotive, and covering it with engineered fill typically costs between $10,000 and $25,000. The railroad controls the timeline, eliminates ongoing storage costs, terminates insurance obligations, and removes the liability from active property. The economic comparison becomes stark. Spend $75,000 to $200,000 for proper scrapping with uncertain timelines and complex logistics, or spend $20,000 for permanent disposal with immediate resolution. The regulatory environment surrounding locomotive disposal extends far beyond asbestos concerns, creating a maze of federal and state requirements that reinforces burial as the path of least resistance. The Environmental Protection Agency's regulations under the Toxic Substances Control Act govern the handling of polychlorinated biphenyls, synthetic compounds widely used in electrical transformers, capacitors, and hydraulic systems before their ban in 1979. Locomotives built before that cutoff date almost universally contain PCB contaminated components, with concentrations often exceeding 50 parts per million, the threshold requiring specialized disposal protocols. Unlike asbestos, which remains relatively stable if undisturbed, PCBs can leach into soil and groundwater, creating long-term environmental liability that follows the railroad regardless of who performs the scrapping. The Resource Conservation and Recovery Act imposes additional layers of complexity, classifying locomotives as potential sources of hazardous waste requiring cradle-to-grave tracking. Every gallon of waste oil, every PCB capacitor, every lead-painted component must be documented, manifested, and delivered to appropriately licensed disposal facilities. The paperwork alone requires specialized environmental compliance staff, and errors in documentation can trigger substantial fines. Railroads operating across multiple states face varying interpretations of federal regulations, with some states imposing stricter requirements than EPA baselines. California's Proposition 65, for instance, creates additional notification and handling requirements for materials containing lead, cadmium, and other listed substances. A locomotive being scrapped in California faces regulatory hurdles that wouldn't apply to the same unit processed in Wyoming or Montana. State-level environmental agencies often require comprehensive site assessments before accepting any industrial waste disposal, even at licensed facilities. These assessments evaluate not just the locomotive itself, but the potential for environmental impact during transport and processing. In states with stringent groundwater protection regulations, scrapyards near aquifer recharge zones may be prohibited from accepting contaminated equipment entirely, regardless of their technical capability to process it safely. This patchwork of regulations means that a locomotive retired in one location may have no viable scrapping options within economically reasonable transport range. Lead paint presents its own regulatory challenges. Most locomotives built before 1978 carry multiple layers of lead-based paint applied during original construction and subsequent repainting over decades of service. The lead renovation, repair, and painting rule requires specific training, containment procedures, and waste handling protocols when disturbing lead paint on any surface. Cutting through a locomotive's steel body with torches or shears aerosolizes lead particles, creating both worker exposure risks and environmental contamination. Proper containment during scrapping operations requires enclosed facilities with air filtration systems, adding infrastructure costs that many scrapyards cannot justify for occasional locomotive contracts. Diesel fuel residue compounds the hazardous waste burden. Even after tanks are drained and fuel systems purged, locomotives retain diesel in inaccessible pockets throughout the fuel delivery system, impregnated in absorbent materials and coating internal surfaces. This residual petroleum triggers requirements under various state underground storage tank regulations and petroleum product handling statutes. Some jurisdictions classify retired locomotives as abandoned storage tanks. If fuel residue exceeds certain thresholds, imposing cleanup requirements designed for gas station remediation on equipment never intended for such classification. Coolant systems present yet another concern. Ethylene, glycol-based engine coolants while less toxic than many other substances in locomotives, still require proper collection and disposal. Over years of service, these coolants become contaminated with heavy metals leached from engine components, transforming a relatively benign fluid into regulated waste. The volume involved, often hundreds of gallons per locomotive, and the contamination level make simple disposal impossible. Burial, when properly executed, transforms these regulatory nightmares into manageable engineering problems. Modern locomotive burial sites are not casual dumping grounds, but engineered containment systems designed to meet or exceed landfill standards. Sites are selected on railroad-owned property with favorable geology, typically in areas with deep water tables and low permeability soils. Before burial, pits are excavated and lined with impermeable barriers, often high-density polyethylene or clay liners that prevent leachate migration. Locomotives are positioned to minimize void spaces, and monitoring wells are installed at strategic locations to detect any future contamination. After placement, units are covered with multiple layers of engineered fill, compacted to prevent settling, and capped with barrier materials that shed precipitation and prevent infiltration. This approach satisfies regulatory requirements for long-term containment while avoiding the multiplying complications of disassembly and transport. Environmental agencies generally accept properly engineered burial as legitimate disposal, particularly when the alternative, improper scrapping or indefinite storage, presents greater environmental risk.